The group SL2Z is the group of 2 by 2 matrices with integer entries where the determinant of these matrices is 1. So AD minus BC equals 1. And what we're going to prove is that this group of matrices is generated by 2 of its elements. T, which is this matrix, and S. This matrix. This pen bigger. So first of all, you can verify that these matrices are indeed in the group SL2Z. And to get started, we're going to notice some properties about these matrices. So first of all, notice that powers of T are as such. So T to the K is just 1K, 0, 1. And S squared is simply the negative of the identity matrix. So it's minus 1, 0, 0, minus 1. We can just check that really quickly. So 0 minus 1, 1, 0. 0 minus 1, 1, 0. Minus 1. That's 0. That's 0. And that's minus 1. So that's true. Okay, so to prove that this group is generated by these 2 elements, we're going to consider an arbitrary matrix in the group. M equals A, B, C, and D. And what we're going to do is we're going to, by multiplying M by powers of T and S, we're going to change this matrix to one where the bottom left entry is 0. I'm going to show you how we do that. So first, let's first notice what happens when we multiply this matrix by S and powers of T. So SM is going to be, so remember S is 0 minus 1, 1, 0. So SM would be 0 minus 1, 1, 0. Multiplied by A, B, C, D. So this is going to be 0, this is going to be minus C. A minus D, B. So notice that when we multiply S by a matrix, it's the same as swapping the 2 rows and then negating the new first row. Cool. And if we do T to the K times M, let's see what we get. We get, so A plus KC and C, and we get B plus KD and D. And so multiplying a matrix by T to the K transforms it in this way. Okay. So now, let's say we have A, B, R, M, A, B, C, and D. We can assume, without loss of generality, that the modulus of A is greater than or equal to C, the modulus of C. As in the magnitude of this, the top left entry is larger than the magnitude of the bottom left entry. The reason, if this isn't true, then what we can do is just apply the matrix S to M. And as you see, we will end up swapping these two. And so now the magnitude of the top left entry is greater than the magnitude of the bottom left entry, if it wasn't already the case here. So we can assume that our top left entry has a greater magnitude than the bottom left entry. If it doesn't, we can just apply the matrix S and make that the case. So using the division algorithm, because this is true and A, B, and C are integers, we can say that A is equal to Q times C plus a remainder, where the remainder is greater than or equal to 0, but less than C. Or you could also say magnitude of R is less than the magnitude of C. Okay, and so this means that R equals A minus QC. And so we can write now our M as So now what we can do is if we apply T to the minus Q to M, what are we going to get? So we're going to get A minus QC, B minus QD, C and D. Notice that A minus QC is just R. So this is R, B minus QD, C, and D. And now what we can do is we can apply S. So we have S, T minus Q, M. And so now we swap both, so R, B minus QD, and negate the top, so minus C, minus D. And remember, because C, the modulus of C is greater than the modulus of R, we can use the division algorithm again. And we can say minus C is, we'll call it Q1 this time, is Q1R plus another remainder R1, where R1 is greater than or equal to 0 and less than R. In other words, R1. The modulus of R1 is less than the modulus of R. And then again, we can isolate R1 and swap it back in. And we can repeat this process over and over again of applying. So the next step would be to apply the matrix T to the minus Q1. s t to the minus q m, and we would get something else, and we'd be able to apply the division algorithm again. The point is, with the division algorithm, you're eventually going to get, if you keep on applying it, you're going to get r, you're eventually going to get r as your remainder is 0. So eventually we're going to have this as 0 as we keep on iterating this process. And so that will mean that when we apply the t to the q minus 1, we're eventually going to have a top left entry of 0. Something's here, something's here, something's here. We're eventually going to have a top left entry of 0. And then what we can do is we can apply the matrix S, and it will swap the rows. And so this 0 will go into the bottom left corner. And so successfully, just by applying just by applying powers of t and s and so on and so forth, we have transformed M into this new matrix that has a bottom left entry of 0. Cool. And this matrix is in the group SL2Z. And so it must have determinant 1. And so alpha delta minus beta times 0 is 1. Beta times 0 is just 0, so this means alpha delta is 1. But both alpha and delta are integers, and so we either have alpha delta both equaling to 1, or they both equal to minus 1. In each case, so let's consider the first case. In the first case where they're both equal to 1, we have our new matrix as 1, 1, 0, beta, which, if you remember from before, is just t to the beta. And so in this case, we have our original arbitrary matrix M multiplied by some powers of t and some powers of s, whatever, equals t to the beta. And so we can, in this case, we can multiply by the inverse of this. And we've expressed our arbitrary matrix M as a product of the matrices S and T. However, if, so that's this case done for. This one will have M equals minus 1, minus 1, this. This is simply just negative 1, 1 minus beta 0, which is the same as the negative identity multiplied by 1 minus beta 0, 1. But remember from before, the negative identity is just s squared. So if we scroll back down, this is equal to s squared, and then this is just t to the minus beta. And so we have this matrix M equaling S squared times T to the minus beta, but this M tilde is just equal to M multiplied by some powers of S and T. And so if we multiply by the inverse of this, we have M equaling some inverse of this multiplied by S squared T to the minus beta. And so in each case, we have expressed M as powers of the matrices S and T. And so that is job done. That is the proof complete.